Z4, and so on. In order for this matrix element to be non-vanishing, we have to return to our original state at the end of the operator string. Okay. So you can think of this as really a sum over closed loops in this many-body Fock space, or many-body Hilbert space. Yeah. And we want to be able to interpret this as a sum of probabilities. So we want each of these terms in this summation to be positive. So what condition can we impose on our Hamiltonian to make this the case? Well, the usual condition that people impose is something known as stochasticity, which requires that every matrix element of each of these Hamiltonian terms is real and negative. Okay, and if this is true, then we have this, negative 1 to the n. Each of these minus signs from here cancels the -1, and that ensures that each of the terms in this expansion is positive. Yeah. Now, if this condition right here holds, then by the Perrin-Frobenius theorem, this implies that the ground state can be made to have all positive entries. And this is where the wave function non-positivity comes into play. If a phase of matter cannot be written in a local basis where we have all positive entries, then it cannot arise from a stochastic Hamiltonian. Right. So stochasticity is a sufficient but not necessary condition for each of these terms to be positive. Hopefully it's clear from the way I've drawn this cycle right here that it's possible to imagine a case where each of these individual terms in the Hamiltonian has some non-trivial phase, but all these phases always manage to cancel out in any closed cycle. Okay? And this is precisely the loophole that was pointed out a few years ago, the possibility of this sort of cancellation of phase factors. Now, it's easy to see that this is true, but it's also clear why it hasn't really been employed too much, right? Stochasticity is simple to state, it's simple to check. This is a much more complicated condition to demand of your Hamiltonian. Now, you can make some progress by noting that the sign structure of these loops is preserved under a many-body basis rotation. So if I take each of these basis states and I rotate it by a phase factor, e to the I theta j, all these phase factors cancel out, and the total sign associated with this loop remains the same. Okay? So what this means is that if our Hamiltonian can be made stochastic by these many-body basis rotations, then all of its non-zero cycles will have a positive entry associated with it, and there will not be a sign problem. And in fact, you can prove that this is an if and only if statement. If all these cycles have a positive contribution, then there exists a many-body basis rotation that takes you to a stochastic Hamiltonian. Right? Now, right away, you should see from this condition right here that it already seems to suggest a very sharp difference in how we talk about the sign problem. Right? Essentially, the condition is if our Hamiltonian can be made stochastic by a many-body basis rotation, then there's no sign problem. But if we think back to this condition of ground state positivity, well, if we're allowed to do these many-body basis rotations, you can always trivially make a ground state positive, right? So if the condition is stochasticity modulo these basis rotations, it would seem to be that this wave function positivity is a completely irrelevant property. And indeed, what we'll show in this presentation is that there exist models of systems that have wave function non-positivity, but are still sign problem free through this condition right here. Yeah. So to summarize what I said in the previous slide, Hamiltonian is sign problem free if it can be made stochastic via a many-body basis rotation. And this kind of outlines the general strategy that we're going to use in constructing these sign problem free models of twisted quantum doubles. So what we have here on the right-hand side are stochastic models. So for any discrete group G, we can construct a stochastic Hamiltonian that lives in the trivial gapped symmetric phase of this symmetry group. We can then gauge this Hamiltonian, preserving the stochasticity to obtain a untwisted quantum double theory. This is something like the toric code if your group is Z2. Okay. Now going over to the left-hand side over here, we have symmetry protected topological phases. Right? These are phases that can be related to a trivial phase by a local unitary transformation. Okay? This local unitary transformation relation is well known, but what hasn't really been stressed is that these local unitary transformations are exactly these many body basis rotations that preserve the structure of the sign problem. So this immediately renders these SPT phases sign problem free, despite them being non-stochastic. Okay. We can then gauge these SPTs to obtain a twisted quantum double, something like the double semion theory. This local unitary can also be gauged. Once you do this, you obtain some horrendous non-local unitary transformation. It's some, mess of Wilson loops and Wilson lines and whatnot that relates these untwisted and twisted quantum doubles. But importantly, just the existence of a unitary transformation ensures that these twisted quantum doubles are sign problem free. You never actually have to do these transformations. You just need to know that one exists in principle. As a warm-up, I'll work through the example where the group is Z2. This corresponds to the Levin-Gu symmetry-protected topological phase, which you can then gauge to get a double semion theory. And then I'll outline the general argument for a general discrete group. Okay. So I want to start by showing that the Levin-Gu model is sign problem free. So what is the Levin-Gu model? It's a model of a Z2 SPT in 2 dimensions. It's defined here on a triangular lattice, and it consists of a sum of local terms. Each term is just a Pauli X operator multiplied by this sort of complicated phase factor right here. And it's easiest to explain in pictures what this phase factor here does. The idea is that given a configuration, if flipping a spin J changes the number of domain walls by an odd amount, this phase factor here assigns a factor of -1. Okay? So for example, if we start with a fully polarized state and flip spin J, right, we go from 0 domain walls to 1. This gives us a factor of -1. If we then flip a neighboring spin, this flip doesn't change the amount of domain walls, so the phase factor associated with that is just +1. Okay. So this is a Z2 SPT, 2 + 1D. And just right away from these pictures, you can see that every term in the stochastic series expansion is going to be positive, right? Because if we look at a non-zero matrix element term right here, we start with the state Zj, we act on it with a bunch of spin flips, eventually getting back to our initial state. If we're going to get back to our initial state, the domain wall parity has to change an even number of times, right? And the fact that it changes an even number of times means that these minus signs always cancel out. And the net sign of all these terms is always going to be 1.
Question?
Yeah.
There's also a minus sign from the minus beta, as you mentioned before. Is that unimportant here?
Yeah, so generally there's going to be a minus sign in front of all our terms in the Hamiltonian right here. Right, you can see there's this minus term right. Yeah, you shouldn't worry too much about this -1 to the n, because there's always going to be a minus sign in front of our Hamiltonian terms that takes care of that.
Okay, thanks.
Yeah, you can pretty much just forget about that. We'll really be interested in the contribution being positive. Right, so this shows that the Levin-Gu model is sign problem free. It can be shown more easily by the statement that this was related to the Ising paramagnet, which is just this without the phase factor, by this unitary transformation right here, which is a diagonal unitary transformation that assigns a factor of -1 to all basis states with an odd number of domain walls. So it just measures the domain wall parity and gives you a -1 if it's odd. Okay. And this is the standard SPT entangler that takes you from a trivial state to an SPT state. Okay. So this is sign problem free, but it is an exactly solvable model. So you might wonder why this is a terribly interesting thing. Well, you can show that this sign problem freeness is actually preserved under a number of non-integral perturbations. So for one, you can perturb it with sigma z interactions. This is quite a generic property of the stochastic series expansion, where any diagonal perturbation preserves the sign structure, right? So we can add sigma z, we can add sigma z, sigma z, we can add, any amount of complicated interactions, as long as they're diagonal, that will preserve the sign structure of the stochastic series expansion. And adding in, for example, a sigma z term will give us a transition into a Z2 symmetry broken phase. We can also add in just the, yeah?
Here the symmetry is generated by sigma x.
Yes.
So if I add a sigma z, then the symmetry is already gone.
Yeah, so what I'm imagining is like an Ising term, like a sigma z term.
I see.
Yeah. I mean, you could add in sigma z if you wanted to, and ask what that does to your system. Like that will still preserve the sign problem, but it's as you point out, that's not the most interesting term that you can add. Slightly more non-trivially, you can actually add a sigma x perturbation that gives you a transition between the trivial and non-trivial SPT phases. So you can study this transition between trivial and non-trivial SPT phases while preserving sign problem freeness. Now, what I want to do is I want to gauge this Levin-Gu model to obtain the double semion model. And this is done in kind of the standard way, right? So the standard minimal coupling procedure is we introduce qubits to all the links of the lattice. Sigma x operators remain the same. And then if we have a sigma z operator, we add on a string of gauge operators that connect the two ends of the operator. Okay. So this gives us our double semion Hamiltonian. This consists of 3 terms. The first is precisely the term that came from the Levin-Gu Hamiltonian, now with this tau z connecting the phase operators. We now introduce a new term, the product of tau z's around each plaquette, which suppresses gauge flux. And then we have a Gauss law term, which we just impose energetically. And this should be contrasted with the toric code Hamiltonian, which is exactly the same thing, but just with these phase factors missing. Okay. Now, this toric code model down here is stochastic. So the question we want to ask is, does there still exist a diagonal many-body basis rotation that takes us from this toric code to the double semion Hamiltonian? Now, if you recall this unitary transformation that we discussed earlier, this unitary transformation cannot be decomposed into symmetric local gates. That's kind of the definition of an SPT phase. However, the entire unitary transformation regarded as one giant non-local transformation is globally a symmetric operator. So you can, in principle, take this operator and gauge it to obtain some gauged operator tilde u. Okay. So this begs the question, does the equality between the two phases stay preserved under gauging? Right, so does this gauged operator U map the double semion model to the toric code in the same way the ungauged version mapped the Levengood model to the trivial Ising pair magnet. And this is not generically true, right? If you have some operator equality, that equality is not necessarily preserved under gauging. A simple example is this right here, right? So we have Zj, Zk, Zk, Zl, Zl to Zj in the ungauged model, right? In the ungauged case, we could just expand everything out, and this gives you 1. But if you gauge each of these operators, the gauged version gives you a closed Wilson loop that wraps around from sites J to K to L to J. Okay. So more generally, the statement is that equalities are preserved up to closed Wilson loops, right? So operator equalities are preserved in the subspace where there are no gauge flux excitations. But generically, if you take an operator and then gauge it, you might obtain stray factors of Wilson loops, right? So if we take a particular term in the double semion Hamiltonian and apply this gauge unitary transformation, we'll get the corresponding term in the toric code Hamiltonian up to this sort of stray factor of Wilson loop operators that might appear. The exact form of this Wilson loop operator will depend on our gauging convention. Okay. So what we've shown is that the double semion model is related to some very complicated non-local version of the toric code with all these stray Wilson operators floating around. Now, I want to argue that this is not a problem. So I'm going to argue that we can apply additional unitary transformations that sort of clean up these Wilson loop operators and ultimately give us a unitary transformation that relates the double semion model to the toric code. But I do want to emphasize that even if I stopped here, even if this was all we could show, this would still provide a counterexample to the previous statements in the literature about the existence of the sign problem in the double semion model. Because what I can do is I can impose, I can restrict myself to a subspace where there aren't any gauge flux excitations. And in this subspace, the toric code and the double semion model are directly related by this gauge unitary right here. So if I restrict my subspace in this way, what I should find is that the double semion model is sign problem free, despite still having a intrinsically non-positive ground state. So this still gives a counterexample, but I want to show that you can still do better and simulate the entire double semion model, including gauge flux excitations, without a sign. Great. So I want to argue that you can apply additional unitary transformations to remove these stray Wilson loop operators right here. And this is unfortunately a very complicated argument. I wish I had a more physical way of explaining it in terms of like error correction or gauge excitations or something like that. But at the end of the day, the unitary transformation that fixes these stray factors is just some very complicated many-body transformation that I will attempt to explain in the presentation, but I think it's difficult to do it justice in a slide or two, right? Now, the key point to argue is that these stray Wilson loop operators respect the group structure of Z2, which is to say they correspond to the non-trivial Z2 element, and they necessarily square to the identity, right? So these stray factors are always plus or minus 1 and can be in principle removed via additional basis transformations. And I do this in the following way. So I start with some generic basis state that I just pick as a starting point. I then flip the first spin, okay? This gives me a new state, and the term in the Ising model has this sort of stray Wilson loop factor, F1 of C. Okay? I then rotate this basis state by F1 of C, and that absorbs the stray factor in the Ising operator into our basis state. Okay? And the idea is that you can just iterate this procedure over your entire Hilbert space. You can take these stray factors and just absorb them directly into your basis states in a way that is self-consistent and doesn't mess up other terms in your Hamiltonian. Okay. And again, this is a very complicated argument that you need to do very carefully in order to get right, but it turns out that you can do this, which then implies, right, that the double semion model and toric code Hamiltonian are related by some complicated many-body basis rotation. And the existence of such a transformation implies that this double semion model is sign problem free. So I did this by a kind of a complicated argument, so you might naturally be suspicious, and of course I certainly was as well. But you can actually do this explicitly. So I just did the simulation, right? I could take a 4x4 lattice. I explicitly expand out our double semion Hamiltonian and just start randomly picking out terms in the partition function. And you can just see, right there on your computer that they all turn out to be one. We have these complicated phase factors that always manage to cancel out at the end of the day in the double semion model and give us a sign problem-free stochastic series expansion. As I emphasized before, this is not a result that is restricted to the exactly solvable limit. So any diagonal perturbation that we add to our Hamiltonian will preserve the sign structure. Now, adding in these diagonal perturbations will generically proliferate anions in the theory. In this case, it'll proliferate a semion-anti-semion pair, which you can then condense to get a trivial state. And this is some topological phase transition that can be sign problem-free quantum Monte Carlo.
I think I have some basic question.
Yeah.
I think previously what you told us is if we have a many-body basis and we do a phase rotation, we preserve the sign structure. Now what we are doing is a unitary. If I want to diagonalize this unitary in a many-body basis, that basis would be pretty complicated. And do you mean this doesn't matter?
No. So, yeah. So maybe I was being a little bit sloppy with my words. What I am showing is that these two are related via a diagonal many-body basis rotation. So the unitary that we're constructing is diagonal in the computational basis. In the computational basis.
I see.
Just the standard SC basis, right? And that's a highly non-universal property, right? Like no one, for example, for SPT phases, right? Like the fact that this SPT entangler happens to be diagonal in the computational basis, that's not a universal statement that really you would think has much physical meaning. But the fact that it happens to be the case and kind of the natural computational basis is what allows these SPT models to be sign problem free.
I see.
And then you can show that this diagonality is preserved upon this gauging procedure.
I see. And this works for all the group cohomology SPTs in 2D.
Yeah, so I mean that was exactly what I was going to show in my next slide right here.
I see.
Although it's, as you'll see in the next slide, the argument is basically the same. Nothing new happens. As far as I can tell, this should work in higher dimensions as well. I don't see any obstacle for this not working in higher dimensions either. Okay, so as I was saying before, these perturbations will drive anion condensation, and you can access these non-integrable topological phase transitions through these sign problem-free models. Yeah. So now I want to generalize this to generic group cohomology, discrete SPT phases. I will go kind of fast over this because there really isn't anything new. It's essentially the same argument as before. You need to be a little bit careful about the non-abelian case. You have to kind of think hard and make sure there aren't any subtleties that the non-abelianness causes. But as far as I can tell, the argument goes through just fine for non-abelian states. So for a discrete group G, we want to define our model of discrete SPTs in terms of group valued qubits. So the Hilbert space on each site has elements labeled by the group elements of our group. We have a generalized poly X operator defined with some group element H that acts on our states by left multiplication. And then we have the generalized poly Z operator, which given some particular representation, gamma, just gives us the matrix element of the corresponding group element in that representation. Okay. In this generalization, we have the corresponding trivial stochastic paramagnetic state, which is just the sum over all generalized poly X operators. This is stochastic and has as its ground state an equal weight superposition of all states. Okay. We then have, we can then write down this fixed point SPD Hamiltonian, which just like the trivial paramagnet is an equal weight sum over all basis states, but with a particular phase associated with each basis state. And you get this from computing cocycles, defined in the group cohomology of this group. Okay. So you can map this SPT Hamiltonian to the trivial Hamiltonian via a diagonal many-body basis rotation. This diagonal many-body basis rotation is precisely this factor in brackets right here. It essentially just attaches each of the corresponding phase factors to each of the basis states. So if you apply this on a Hamiltonian level, this maps these x's to the corresponding b's, something like the terms that appeared in the Levengood Hamiltonian. Okay. And because this SPD Hamiltonian is related to the trivial state by this diagonal transformation, this SPD Hamiltonian is also going to be sign problem free. We can then gauge these Hamiltonians to get twisted quantum doubles. We again do this through the standard minimal coupling procedure. We attach group valued qubits to the links of the lattice. Our poly X operators remain the same. If we have some Z operators, we attach a string of gauge Z operators that connect the two. Our twisted and untwisted Hamiltonians again consist of gauged terms arising from our SPT phases. We then have a term A, which enforces flatness of the gauge field, and then a Gauss law term. Okay. And the claim, once again, is that these twisted and untwisted quantum doubles are related by some diagonal many-body basis rotation, which you can get, once again, by just gauging this SPT entangler U that mapped us between the trivial and non-trivial SPT phases. There's once again the subtlety that this correspondence, once you gauge it, only holds up to Wilson loop operators. There's generically some stray Wilson loop operators that appear when you just naively gauge the unitary transformation. But once again, you can apply successive basis rotations that remove these Wilson loop operators, thereby establishing a correspondence between the twisted and untwisted quantum double. Okay. Right. So this sounds convincing, but again, it's a complicated argument, and it's worthwhile to have an independent verification. Just like with a double semion model, where I sat down and explicitly simulated the Hamiltonian. And you can actually do this via a parallel method of verifying the sign problem freeness. Okay. And we do this by studying these exactly solvable constructions of twisted quantum doubles described in this paper right here in 2013. So they construct stabilizer models of twisted quantum doubles that are essentially just, if you want, you can think of them as parallels of the toric code Hamiltonian generalized to a twisted quantum double. So in these models, our Hamiltonian consists of two terms. We have these plaquette B terms, which enforce flatness of the gauge field, as well as these terms on each vertex A, which essentially take each of these sites and act on them with the group element G. We can also obtain a Hamiltonian like this from the previous slide by just projecting out the matter fields and getting a Hamiltonian that only acts on the gauge degrees of freedom. Right? There are non-trivial factors in this vertex term, and that encodes the non-trivial twist of our quantum double. Okay? Now, these Hamiltonians are exactly solvable, which means that these terms H obey these nice algebraic relations. They commute on different sites and obey the group composition law on the same site. And because we have this exactly solvable Hamiltonian that we can do so much with analytically, we can just explicitly evaluate these QMC terms by hand, right? In other words, the stochastic series expansion is tractable analytically. And I can just, write out every possible contribution to the QMC expansion and verify using not terribly complicated math, but something that is maybe a bit too involved to show in a presentation, that all of these contributions turn out to be positive. Okay. Once again, as I stressed before, I'm showing that this exactly solvable model is sign problem free. But the sign problem freeness is not restricted to the exactly solvable model. I can always perturb this by a diagonal perturbation that breaks the integrability but preserves the sign structure. So generically, any diagonal perturbation will give you some non-trivial Hamiltonian for which you can access topological phase transitions and whatnot while preserving the sign structure of these Hamiltonians.
Just to make sure, if I add some non-diagonal perturbation, then there may be sign problem.
Yes.
Mm-hmm.
It's still possible that it'll be sign problem free, but you would just need to check that explicitly.
I see.
Right. So, in that sense, sign problem freeness is kind of fragile, right? You can, there's no symmetry that prevents you from adding these off-diagonal terms. But that's generically the case in these systems, right? Like, even previously when we were talking about stochasticity, there's no symmetry that prevents you from adding a non-stochastic term in your Hamiltonian. You're always going to be dealing with some level of fine-tunedness with these systems. Okay. Right. So what this shows is that there exist sign problem-free models of twisted quantum doubles. And moreover, they aren't some exotic model. They're pretty much exactly the standard models that people have been studying for decades. The only difference is that you have to sort of think more carefully about how you are doing the quantum Monte Carlo. And if you do that, you'll find that even though naively there appears to be a sign, if you properly, do out the expansion, you find that the signs always cancel out, and you can actually do a sign problem-free QMC expansion. So that's a pretty interesting conclusion, right? And I think there are a lot of interesting future directions that you can take this. This project really only came together in like a month, right? Like I had this realization like on a plane flight, end of August, I think, and then the paper came out late September, right? So I think there are a lot of really interesting open questions. The first and kind of most pressing question that you might want to ask is, what really is a true intrinsic obstacle to QMC simulations, right? Like people previously thought there was some intrinsic obstacle to these Hamiltonians. Apparently there isn't. but surely there must be some fundamental obstacle that prevents us from doing something, right? Like if we got to the point of like being able to do a quantum computation efficiently, right? Like you might expect that to not be the case. Um, so, what tools do we have to talk about more fundamental obstacles to QMC expansions? We also might want to think about taking this construction and generalizing it to other phases of matter that were previously thought to have a sign problem. I think the most pressing one really are these chiral phases, and asking is there a way to construct a chiral state that is non-stochastic but nevertheless doesn't have a sign problem. We can also study this within string net models. So using this, you can actually show that abelian string net models are sign problem free. But the question of how this generalizes to non-abelian states is an open question. On kind of a more physical level, I think it's important to think more generally about how we want to construct non-stochastic Hamiltonians that turn out to be sign problem free through this construction right here, right? So, I mentioned in the introduction, we have all these no-go theorems over the past decade ruling out certain phases of matter. These no-go theorems still are useful, right? And that it says, if we want to construct some physical spin system, some more realistic Hamiltonian that realizes the double semion model, for example, the Hamiltonian has to be non-stochastic. And we don't really have good methods of designing non-stochastic Hamiltonians. Like, really the only people who have really done it are like me and this Ite Hen person, right? So there's a lot of work that can be done there, I think. I briefly alluded to this, but this is a construction that should work in higher dimensions as well. I'm not immediately aware of anything super interesting that happens there, but that's definitely something that's worth continuing to think about. And then the final question, kind of more practically, is what sort of interesting questions does this immediately let us access, right? Like we understand the double semion Hamiltonian, the double semion phase of matter quite well. But is there some really unconventional topological phase transition, something that we don't understand that well, that this construction lets us access? Okay. So those are sort of future directions that I'm thinking about, and I'm happy to answer any questions on it.
Yeah,
Thank you,
hi.
for the very interesting talk. Yeah, further questions?
Yeah, I have a question.
Yeah.
Can you hear me? Okay. So I'm wondering, what is the difficulty to applying the current method or the current argument to the string net models?
Yeah, so there really isn't any difficulty. Like applying this to string net models is absolutely doable, and it is seemingly a straightforward computation. It's just one that I haven't gotten around to doing.
Right, I see.
Like I've done it for abelian string net models, like that's easy, but showing it for the non-abelian case is a little bit more complicated, but an absolutely doable computation.
By saying abelian, you mean the abelian topological order, right?
Yeah, abelian topological order.
I see. And there are still some cases where you can have non-commutative categories. For example, the Hagerup category, where the anyons do not the label of anyons, the fusion of anyons do not commute. Then do you see any obstruction to applying the method to these cases?
Yeah, so I mean, I guess there are two there are sort of two different methods that I'm using in this work, right? Like you have the first method, which is we have some stochastic model in mind, right? Like we have the untwisted quantum doubles and the twisted quantum doubles, and we're finding transformations that map us between the two, right? So that's one approach. And for something like the Hagerup that you mentioned, I'm not aware of like sort of a corresponding trivial model that you might try mapping it to. But you can also try taking this approach right here, right? Is if you have some exactly solvable stabilizer model, you might have enough analytical control that you can just verify what the QMC looks like explicitly. That just turns out to be a doable computation where you can check whether or not some non-trivial sign appears. And then once you establish the lack of a sign problem in the exactly solvable case, you can always perturb it with these diagonal perturbations to get something more non-trivial.
I see. So if the StringNet model turns out to be, just a conjecture. If the StringNet model turns out to be not sign problem free, then if I want to construct some sign problem free model, does it mean that we need to know, for example, some ungauged version of the topological order to construct such a model according to your
yeah, so I think for string net models, if we're taking this approach of trying to find some sort of mapping between it and a stochastic model, I think the corresponding stochastic model would just be the string net model if you set all the f symbols equal to 1. Right?
Okay.
So that's the string net model with for some given set of anion labels with trivial f symbols. That's a stochastic Hamiltonian defined on the same Hilbert space as your string net model. And you can see if you can construct a unitary transformation that gives you these non-trivial f symbols.
And if all f symbols are set to 1, that means you don't have any fusion structure.
Exactly.
You don't have any non-trivial fusion structure.
Yeah. So the question is, can you add this non-trivial fusion structure in through these many body basis rotations?
I see. Is it possible?
It might be. I'm not sure. Yeah, it is for abelian.
Okay.
For abelian string net models, it is. For non-abelian, I'm not sure.
It's possible.
Yeah, because these many body basis rotations are quite complicated, right? Like they're generically very non-local transformations.
Yeah.
So the question of what you can do with these unitary transformations is not immediately clear to me.
I see. Thank you very much.
I have a question about the question just now. You said in some cases the fusion of anions is not commutative.
Yeah, it is. Yeah.
But isn't it supposed to be commutative?
Not always, I should say. Yeah, for most of the cases we are considering, yes, it's commutative, but there can be some categories where the fusion is, by definition, not commutative. And in these cases, if you want to put them on the level 1 model, you need to carefully obey the orientation of the lattice and define those those terms according to the orientation. Yeah.
Within a modular tensor category, is fusion commutative?
I'm not sure if the non-commutative category gives modular tensor category. I'm not sure. Oh, sorry. I should say it like this. So, what you put on the level 1 model is a fusion category, and this fusion category can be non-commutative. The output tensor category is still a modular tensor category.
Yeah,
which means it's commutative.
Modular tensor category, the fusion becomes
commutative. Yeah. That means the output topological order is still modular, and which means the fusion is still commutative. But the input fusion category can be non-commutative.
Then I have one more question. Just want to make sure, in the previous literature, you said people had the no-go theorems for the positivity of the wave function. Should I understand it as those no-go theorems are still correct? They are just no longer relevant for whether there's a sign problem. Is this the way to understand it?
Yeah. So that's exactly the way that I understand it. Like nothing, there was no error in these no-go theorems, right? Like it is still true that these phases of matter cannot have positive wave functions.
Mhm.
The place where the conclusion differs is just the statement that there can be sign problem-free Hamiltonians with non-positive wave functions.
Mhm. And also, even within this talk, the basis to perform Monte Carlo calculation you consider is still the computational basis. In
Yes, it's
principle, I can also consider something a little bit more complicated, right? Say maybe the nearby two qubits can have some entanglement.
Mhm.
Uh, does that help to remove some of the sign problems?
Um, yeah, so I mean, yeah, so I mean, sort of on a theoretical level, that can help, right? So if I take my sign problem-free Hamiltonian, like if I take this Hamiltonian right here, right? And I apply some local unitary transformations that kind of entangles nearby sites, right? Um, yeah, I get some transformed Hamiltonian that does have a sign problem in the computational basis, but wouldn't have a sign problem in the slightly entangled basis.
Mhm. Then, uh, then if I am allowed to use that kind of basis, will the presence or absence of a sign problem somehow related to whether such a state can be exactly represented using a finite bond dimension tensor network?
Um, I'm not immediately sure how that would follow. Um, could you
I
maybe
also don't
elaborate on why
know.
you would think that would be the case?
Uh, Clearly, I didn't think it through in any sense. I just
Um,
feel the tensor
I mean,
network is imposing some entanglement for some nearby sites. Uh,
mhm. I mean, it could be true. I'm not super familiar with tensor networks. I know there's a lot of literature on representing these twisted quantum doubles with tensor networks.
mhm,
Um, so there could definitely be something there, but I'm very much not a tensor network person. So
mhm. I also need to think more about it.
mhm.
Yeah, does anyone else have other questions?
Yeah, I have another question.
Yeah.
So you also mentioned I think you also mentioned anion condensation somewhere in the slide. And
Mhm.
um, so for simplicity, let's consider if my model has a gap boundary, which is
Mhm.
described by the anion condensation,
Mhm.
then do you think that the argument or the approach will go through directly?
Um, yeah, so I mean, the sorts of perturbations you can add um, don't let you access generic anion condensations. Um, so
Right.
in particular, in this language, what these diagonal perturbations allow you to do is to proliferate magnetic flux excitations. Um,
Yeah.
so you can condense flux anions,
Yeah. Yeah. Right.
and that lets you, get some subset of topological phases. I think I wasn't able to find a place where this was proven, but I think if I start with a twisted quantum double and I just condense flux excitations, the only other phases I get are other quantum doubles of some like subgroup. I
Yeah.
don't think you get anything different from that. But yeah, you can only access those phases with this method.
Um, yeah, but in the case of gap boundary of or a gap domain wall, yeah, you will have two different phases
Mm-hmm.
on the two side of the boundary of
Yeah,
the domain wall maybe. Then, but
yeah.
what about the one-dimensional domain wall? Can we
Hmm.
guarantee that in the presence of the domain wall, it is still sample free? So,
Um,
maybe, yeah,
yeah. So I mean, I'm not sure off the top of my head. I think you would have to check. I mean, I think
okay,
if you if you just try these models with open boundaries, I think you run into problems. But there could still be a construction there. I'm not certain.
Okay, thank you.
Okay, any other questions?
Yeah, I have a question about what you said, the perturbation sigma x and sigma z are preserving the science structure, but they cannot be both diagonal in the same basis.
Yeah. So I mentioned that, right? So I said that diagonal perturbations preserve the sign structure, so the sigma z perturbation is safe. The fact that in this case, the fact that the sigma x perturbation preserves the sign structure is a separate kind of special case.
What do you mean by a special case?
As in, it's not obviously true that this is sign problem free.
But I think you said it is a diagonal perturbation, right?
No. So diagonal perturbations always preserve the sign. Yeah. So sigma z preserves the sign structure. Non-diagonal perturbations can preserve the sign problem free.
But they don't have to.
But they don't have to. This is a special case where it does still preserve the sign problem freeness.
So if both of the perturbation appear, the sign structure is still preserved.
Yes.
Okay, I see. Thank you.
Yeah. And so just to say a few more words about this, the reason why the sigma x perturbation preserves the sign structure is if I add this to our Hamiltonian with some constant c in front of it, let's say, then I can absorb it into this term right here. And all that does is it changes the factors right here from -1 and +1 to like -1 plus c and 1 plus c. Okay. But this cancellation argument where you have an even number of non-trivial terms appearing, that argument still holds. So it retains the sign problem freeness.
Okay, I see. Thank you.
Other questions? Okay, if not, let's thank Leyna again for the very interesting talk. Thank you.
Yeah, thank you for having me.
Yeah, so we will log out of the Zoom. Bye.
Bye.
Record.